limitations, and generalizations of integration. Okay, so far in our exploration of integration, we've been focusing on finding antiderivatives, essentially, reversing the process of differentiation, using the standard formulas we've learned, and also by using a bit of clever inspection to figure things out. But now, it's crucial to understand that integration isn't always a smooth, straightforward process. It's not like there's a formula for every function you'll encounter. There are definite mathematical boundaries and subtle points to be aware of. If we aren't careful, it's easy to fall into conceptual errors. We need to recognize that integration has its limitations, and understanding those limitations is just as important as knowing how to integrate when it is straightforward. In the coming slides, we'll delve into some of these limitations, looking at functions whose integrals aren't expressible in terms of the familiar elementary functions, things like polynomials, exponentials, and trigonometric functions, and also discuss some common pitfalls to avoid. We'll also reinforce the importance of paying attention to details like the variable of integration and the domain of the function. Non-elementary integrals. We've primarily been working with functions whose integrals can be expressed using what we call elementary functions. Now, what are elementary functions? These are the building blocks of a lot of math, things like polynomials. For example, x plus 2 or x squared minus 3x plus 1, exponential functions like e to the power of x, logarithmic functions like the natural log of x dollar, trigonometric functions like sine, cosine, and tangent, and even their inverses like arcsine or arctangent. However, and this is a big however, many continuous functions, meaning functions without any breaks or jumps, actually possess antiderivatives that simply cannot be written as a finite combination of these elementary functions. These are what we refer to as non-elementary integrals. Let's look at a famous example, the function f of x equals e to the power of negative x squared. That is, e raised to the power of negative x squared. You might recognize this function. It's the equation for the bell curve, also known as the normal distribution, which is hugely important in statistics. Now we can calculate the definite integral, the area under this curve, over a specific interval using more advanced techniques, like numerical approximation. But the indefinite integral, that is, the general antiderivative, integral of e to the power of negative x squared with respect to x, cannot be expressed using any of the standard formulas or substitutions we've learned so far. It just doesn't have a nice, closed-form solution using elementary functions. Here's the key takeaway. If you try to find the integral of a function and no standard formula or substitution seems to work, it's a strong indication that you're dealing with a non-elementary integral. Don't get discouraged. In more advanced mathematics courses, you'll learn techniques like using power series, essentially, infinite polynomials, or numerical methods to approximate these integrals. We'll be building on this understanding as we move forward, so keep this limitation in mind. Remember, integration isn't always straightforward, and recognizing these limitations is a sign of a good mathematician. Okay, so let's move on to a really important concept in integration, understanding its limitations. As we've seen in the previous slides, we've been successfully finding antiderivatives, or indefinite integrals, for many functions using standard formulas and techniques. But it's crucial to realize that this isn't always possible. Variable change, dummy variables. The slide starts by saying that the variable of integration, you'll often see it as x, is actually just a placeholder. We call it a dummy variable. Don't let that word dummy throw you off. It just means the letter itself isn't fundamentally important. What is important is understanding that the rules of integration, like the power rule or the rules for exponential functions, stay exactly the same no matter what letter we use. So, whether we're integrating with respect to x, y, t, or even u, the process remains consistent. Now, how do we know which variable we're integrating with respect to? That's where the differential notation comes in. Remember that little dx or die at the end of the integral symbol. That tells us which variable is the independent one. So, if you see die, it means we're integrating with respect to y. Let's look at an example to make this crystal clear. The slide asks us to find the integral of y to the power of 4 with respect to y. We write that as the integral symbol, then y to the power of 4, and then dy. Now let's break it down step by step. First, we identify the variable. The dy clearly tells us that y is our variable of integration. Second, we apply the power rule. You should recall that the power rule states that the integral of x to the power of n with respect to x is equal to x to the power of n plus 1 divided by n plus 1 plus the constant of $. So we have integral of x to the power of n dx equals x to the power of n plus 1, all divided by n plus 1, plus c. Now, to solve our problem, we simply replace x with y in the power rule. So the integral of y to the power of 4 with respect to y becomes y to the power of 4 plus 1, divided by 4 plus 1, plus c. Finally, we simplify that expression. 4 plus 1 is 5, so we get y to the power of 5, divided by 5 plus c, and that's it. We've successfully integrated with respect to a variable other than x. Okay, so let's move on to a slightly different, but very important, concept in integration. As we discussed on the previous slide, not all integrals are easily solvable with the methods we've learned, and that's okay. Now, we're going to look at how the variable we integrate with respect to works. This is a crucial concept, because it shows you that integration isn't about memorizing formulas for specific variables. It's about understanding the underlying rules and applying them correctly, regardless of the variable used. This will become even more important as we tackle more complex integration problems, and as you move into more advanced mathematical concepts, like multivariable calculus, which we'll touch upon later. Domain considerations. Okay, let's move on to slide 4. As we've discussed, integration isn't always a smooth process. Sometimes we run into limitations, and this slide highlights one of the most important, domain considerations. Integration is performed over a specific interval, meaning we're finding the area under a curve between 2 points. And for that area to have a meaningful, mathematically sound value, the function we're integrating, what we call the integrand, must be well behaved on that interval. Specifically, it needs to be defined and continuous. Think of a continuous function as one you can draw without lifting your pen from the paper. If there are breaks or undefined points, we have a problem. Let's look at an example to illustrate this. Consider the integral of 1 over x, which we write as the integral from 0 to infinity of 1 over x with respect to x. Now, what's the standard result for this integral? It's the natural logarithm of the absolute value of x plus the constant of integration. See, we write that as log absolute value of x plus c. But here's the catch, the domain issue. The function 1 over x is undefined at x equals 0. You can't divide by 0, right? So, if our interval of integration includes 0, the integral is invalid. We can't integrate over an interval where the function doesn't exist. That's where the absolute value comes in. We use the absolute value of x, written as log absolute value of x, because the natural logarithm function, log of z, is only defined for positive values of z since x could be negative. The absolute value ensures that the argument inside the logarithm, what's inside the log, is always positive, as long as x is not equal to 0. So, by using the absolute value, we're essentially sidestepping the issue at x equals 0 and making the integral valid for intervals that don't include 0. This isn't just a mathematical technicality, it has real-world implications. For instance, in physics, when calculating gravitational potential, which often involves integrating 1 over r, where r is the distance r must always be greater than 0. If you try to calculate the potential at the center of a point mass, the formula breaks down because you end up with a singularity, a point where the function becomes infinite and undefined. So, always remember to consider the domain of your integrand. It's a crucial step in ensuring your integration results are mathematically sound and physically meaningful. In the next slide, we'll discuss some common mistakes students make when dealing with integration, building on these concepts. Common mistakes to avoid. First, a very common pitfall is assuming every function has a simple integral. Now, we've spent time learning how to find antiderivatives using formulas and techniques like substitution. It's natural to expect a neat, closed-form answer every time. However, as we discussed on the previous slides, that's simply not always the case. Many students get frustrated when they can't immediately find a formula. Remember, there are functions, we called them non-elementary integrals, where the antiderivative cannot be expressed using our standard functions like polynomials, exponentials, or trigonometric functions. We used the example of the integral of e to the power of negative x squared, and explained that while we can calculate the area under that curve, we can't write down a simple formula for the indefinite integral. So don't force it. Recognize when you might need to move to more advanced techniques like power series or numerical methods, which we'll encounter later in your studies. Next, let's talk about ignoring the differential. This is a surprisingly frequent error. When you're integrating with respect to a variable. It's crucial to pay attention to that variable, indicated by the dx, di, or dt at the end of the integral sign. A common mistake is to integrate a function with respect to the wrong variable. Always double-check what that differential is before you apply any integration rule. It seems simple, but it's a source of many errors. Finally, we have neglecting the absolute value in logarithms. This one is specific to integrals that result in logarithmic functions. Remember that the natural logarithm, log of z, is only defined for positive values of z, so when you integrate 1 over x, you get log of the absolute value of x, written as log of the modulus of x. If you simply write log of x, you're implicitly assuming x is always positive, and that's not always true. Forgetting that absolute value can lead to incorrect results, especially when dealing with functions that can take on negative values. Okay, let's move on to slide 5, where we discuss some common mistakes students make when dealing with integration. It's good to be aware of these before they happen so you can avoid them. So, keep these 3 points in mind as you continue practicing integration. Being aware of these common mistakes will save you a lot of frustration and help you build a solid understanding of the concepts. And remember, we'll be building on these ideas as we move forward, so it's important to have a firm grasp of these fundamentals. Key takeaways. Okay, let's wrap up this section on the limitations and generalizations of integration. This slide summarizes the key takeaways we've covered, and it's important you have a firm grasp of these points. Firstly, we have non-elementary integrals. This means that not every function you encounter will have an antiderivative that can be written using the standard functions we've been working with, things like polynomials, exponentials, logarithms, and trigonometric functions. A classic example, as we discussed earlier, is the integral of e to the power of negative x squared. That is, e raised to the power of minus x squared. While we know the area under that curve, the famous bell curve, can be calculated using more advanced techniques. Finding a simple, closed-form antiderivative using our usual rules just isn't possible. Don't get discouraged if you run into these. It doesn't mean you're doing something wrong. It just means you've encountered a function that requires different methods, like power series or numerical approximations, which we'll explore in more advanced courses. Next, we have variable independence. This is a subtle but important point. The process of integration itself doesn't care what variable you use. Integrating x to the power of n with respect to x is fundamentally the same concept as integrating y to the power of n with respect to y. The rules remain identical. It's like saying, I'm finding the accumulation of something, and the something is represented by whatever variable you choose. Finally, and crucially, we have domain awareness. Remember that integration is performed over a specific interval, and the function you're integrating must be defined and continuous on that interval. We saw this with the integral of 1 over x. The integral of 1 over x is the natural logarithm of the absolute value of x, plus a constant. We had to use the absolute value because the natural logarithm is only defined for positive values, and x could be negative. Ignoring this can lead to mathematically incorrect results. Think about real-world applications too, like calculating gravitational potential. You can't have a zero distance, so your integral needs to reflect that limitation. So, to reiterate, be aware of functions with no elementary integrals, remember the integration process is variable agnostic, and always consider the domain of your function. These are the key things to keep in mind as you continue your study of calculus.